Gabriela. She is a PhD in laser physics, and she has been working in both in academy and in commercial environment. So today she will be sharing with us her research journey in both academy and industry, right? So with that being said, you can start now, Gabriela.
Thank you very much. And I feel like this is actually perfect timing, because after Lynn's fantastic talk and then the discussion of oscillating between industry and academia, well, I've done many of these oscillations in my own career. So I will give you today just a very, very quick kind of tour throughout my research career. I'm not going to go into any big detail, but if anyone has any specific questions at the end, feel free. So my name is Gabrielle. I originally come from the UK. However, I've been living in Germany for the past 4.5 years, and I this year became a naturalized German citizen, which I'm very pleased with. I have a background in laser physics and photonics and quantum technology, and I've been involved in lots of different things in both industry and academia. Just a few things about myself. I was selected as one of the World Economic Forum's Young Scientists in 2016, and then as an Optica ambassador in 2019. I became a senior member of Optica in 2020, and I am very heavily involved with quite a lot of different things. For example, the Optica Meetings Council, as well as we started our first mentoring scheme with Optica just this year. So talking about my career path. So first of all, I will just give a sort of broad overview of what I've done, and then I will give an example of the research that I've done throughout in the following slides. So as I said, I came originally from the UK. I was actually born in a small country, part of the UK called Wales. And in 2003, I moved to London to study physics at Imperial College. I stayed at Imperial to complete my bachelor's, then my master's, and then finally my PhD in laser physics. And I'll talk a little bit about that afterwards. But after my PhD, I decided I will try the industry route. And I was awarded a fellowship called the Knowledge Transfer Secondment to work at an Imperial College startup called Midas Lasers. And in this startup, I was basically commercializing the technology that I developed during my PhD into something that could be shipped and sent to customers around the world. I stayed there for a year, and at the end of the year, it got acquired, which I'll talk a little bit about later. And then I went back into research, back to Imperial College under their doctoral prize fellowship scheme, where I started to develop a new type of laser, and then also went on to work with the European Space Agency to develop lasers for space-based remote sensing. In 2017, I moved to Berlin in Germany, and I took up a position as a research scientist at the Max Born Institute. Again, it was sort of laser development, lasers and nonlinear optics. Again, I'll give an example of that later. But honestly, this was when I was really starting to question whether I really wanted to stay in academia or not. I was actually awarded a Marie Curie Fellowship from the European Commission here in Europe. And at the same time, I got an offer to move into industry. So I had a lot of thinking to do, but at the end, I decided I will try the industry route. I was in good contact with a company called M2, because I'd had a collaboration with them while I was at Imperial. And they actually said to me, we're thinking of opening an office in Berlin. Would this be something you'd be interested in, working for us at this office? And I thought, okay, that kind of sounds quite exciting. I might as well give it a go. But they didn't have an office here. So at the time, I set myself up as a small business owner. This was basically a sort of consulting type business. And for about 1.5 years, I was providing consultancy services, mostly just for M2. June 2019, I became a permanent member of staff, and we established an office here in Berlin. I actually left M2 in July of this year. I kind of felt like my career had developed as much as it was going to do at M2. And then I started looking around for new opportunities. And in August, I started for an innovation consultancy company called Eura. However, and this is something that I'm willing to share with you, basically about the trials and tribulations of life and how they can affect you and your decision making and the things that in your enjoyment of life. Basically, I ended up leaving that job after about a couple of weeks because my father was very sick. So right now I am spending half the time back in the UK to try and take care of him a little bit, and then half the time back here in Berlin. I'm looking to basically rejoin the working world in the beginning of next year. So for now, I'm mostly a carer for my father. So I've left here with a nice purple question mark, because obviously, although it's been now 10 years since my PhD, my career hasn't ended. Who knows what will be on the horizon. So now I'll talk a little bit about the research that I've done. So first of all, I talk about my PhD research. I mean, I did some research during my master's and my bachelor's, but the real core research started when I did my PhD. My PhD was, as I keep saying, it was in laser development, so laser physics, but the types of lasers that I was developing were diode pumped solid state lasers. So for those who don't know what that means, it's basically you start off with a crystalline material and laser material, and then you use a laser diode to pump it to excite the laser crystal into lasing. The type of lasers I was developing were very diverse, everything from continuous wave, very high power continuous wave lasers, all the way down to mode locked or ultra short pulsed lasers. The core of my PhD was via the development of a novel mode locking technique called the nonlinear mirror. And I've got a nice picture on the next slide I'll show you that describes how that works a little bit. The photo here is a little bit blurry because I think that's now about 14 years old, and it was a photo that was taken when I was extremely excited when my laser started to work. Maybe you can just about see on the oscilloscope at the top there, the little nice wiggles that happen when you start mode locking your laser. But basically, yeah, I was generating picosecond pulses, multi 10 watts of output power, mostly for applications in the directions of materials processing, but also for sort of biomedical imaging type applications. During my PhD, I managed to get some world records in terms of output power and pulse duration from lasers that were mostly operating around about 1 micron. So the nonlinear mirror technique is not very well known. So typically people would use a CSAM, a semiconductor saturable absorber mirror, to mode lock their lasers, especially at 1 micron. Or for lasers that need very short pulses, people would typically use Kerr lens mode locking. So nonlinear mirror is a little bit of a weird kind of diversion into nonlinear optics combined with a laser. And what it does is, how it works is you put a nonlinear crystal inside your laser cavity in conjunction with a dichroic output coupler. So the output coupler is highly reflecting for the second harmonic of the laser that you're working with, but it also is then partially reflective for the fundamental wavelength. So basically, when you have your intracavity laser radiation going and the first pass through the nonlinear crystal, it generates the second harmonic. In this case, it was the second harmonic of a 1064 nanometer laser. So we're looking at the green light you see here is 532 nanometers. And then this green light gets 100% reflected back towards the nonlinear crystal. And if you get the phase matching conditions correct, you basically then, via difference frequency generation, convert back down to the fundamental. So as far as the laser cavity is concerned, it thinks that it has more of the fundamental radiation than it perhaps should have had. And it ends up being an effective kind of intensity dependent reflector, which leads to mode locking. So it's a little bit of a confusing explanation there. I realize that I haven't talked about this for probably more than 10 years now. But basically, it's an interesting way of mode locking a laser. After I finished my PhD, as I said, I went to do some research in a startup. Now, working in industry is, especially if you're wanting to commercialize groundbreaking science, the challenge is, how do you get all of that complex system inside a portable, small, robust box that you can ship all over the world and trust it in the hands of people who don't necessarily know what goes into it. Which, yeah, there's been some funny stories of how people would used to manage our lasers and how they would hold them and things like that. But it was a very interesting challenge for me to learn. Okay, so the image that you see on the left there, this is not representative of what went into the MIDAS lasers, but it's obviously a little bit pushing it a bit too far. I would say probably about 10% of those optics on the bench there went into a laser that I would develop at the startup, but still, nonetheless, it's always a challenge. So the company was called MIDAS. It had been started by my PhD supervisor, and I had this opportunity to try to commercialize the mode lock laser systems I developed during my PhD. Some of the interesting things that we went through at the very early stages of developing these products was, how do you make it robust enough that when it goes through customs and the box gets thrown around all over the place, when the customer takes it out at the end, it's still going to work. So we would put these laser systems on a trolley, and then we would push it at speed through the car park of Imperial College and over speed bumps, and then try to get it to continue to work when we brought it back to the lab. So that was quite fun. But ultimately, the startup, at the end of a year that I was working there, they got acquired by a bigger company. So MIDAS got eaten up by Coherent, one of the biggest laser companies in the world. That was also a really interesting experience to have. I got insights into the due diligence, the technical due diligence that a bigger company would make when it is trying to acquire a smaller company. And yeah, got to work in the lab while the people at Coherent were watching us very closely. It was a successful acquisition, and then at the end of that year that I spent at the company, I decided to go back into research. So this is when I started working with the European Space Agency. So I ended up being the work package leader for a European Space Agency project. And as I previously said, the project aimed to develop laser sources that could be eventually put up onto a satellite and used in Earth observation. So why would you want to do that when there are already many devices on satellites that basically do this remote sensing type stuff? Well, the problem is they're reliant on having background light, either from the sun or reflections off our planet, and that's not very reliable. The other issue is that the resolution of the basically the thing that you're trying to image ends up not being that great when you're using this passive light from the sun, for example. So using a laser means that you have 24-hour operation, so you're not relying on some external source of light, but by using very short pulses of laser light, you end up getting really nice resolution of the stuff you're trying to image. So one of the really interesting applications that we were working on was developing a laser for altimetry, which is basically, or vegetation LIDAR, they like to call it. And they are basically measuring how dense forests are, how tall trees are, and basically the general makeup of the vegetation that's on the planet. So this is quite good. As you can imagine, it allows you to keep an eye on, for example, deforestation all over the world, and you can much more quickly recognize the early signs of that. So the type of lasers that we were developing for the European Space Agency were, again, these diode-pumped solid-state lasers, but it was using a type of material called alexandrite. And most people, when they think about alexandrite lasers, if they do think about alexandrite lasers, they think of these enormous things that are used in the cosmetic industry. So alexandrite lasers are used for hair removal, they're used for skin resurfacing, like, for example, if you have acne scars or if you have wrinkles that you want to get rid of, that's normally you'd use an alexandrite laser. But really, to have this thing, these are all lamp pumped because they need the really high energy from the laser system, and that ends up being really massive. You can't put that on a satellite that's going up into space. It needs to be really small, it needs to be really robust, and it needs to be really reliable. So that's what we were aiming to do in our diode pumped alexandrite developments. So alexandrite, it's actually a really beautiful crystal. It has this really weird property where it looks a different color, whether you're using sort of natural light or if you're using incandescent light from like an internal lamp or something. So it's very beautiful, and a lot of people like to have it in jewelry. However, as a laser source, it can be tuned between around 700 to 850 nanometers, so very similar to titanium sapphire lasers. But it can be made much more compact because the crystals tend to be a little bit more robust than titanium sapphire lasers, and just a lot more practical. So that during this work, we had demonstrated again a number of world firsts, very high power operation, short pulse generation, and in general, it was just really cool. Like, it's a really beautiful laser. So then, yeah, then I moved to Germany. The main reason for moving to Germany was because of the Brexit election. My husband is also German, and the both of us kind of felt like if we wanted to continue our careers, for example, in academia, it was unclear whether we'd be able to access funding from the European Commission. And so it seemed like a good idea to move to continental Europe. So we did that, and we moved to Berlin. And actually, I started working at a research institute called the Max Born Institute. This was going back in the direction of ultrafast laser science, so back to more similar stuff that I was doing during my PhD, the generation of ultra short pulses. But in this case, at Max Born Institute, I was involved in a project that was developing optical parametric chirped pulse amplifiers. So this is basically, again, nonlinear optics. So using nonlinear optics to generate wavelengths that are maybe not so easy to target with just a standard laser system. And it means that you can also get really, really broad band pulses, so very, very short pulse durations at really exotic wavelengths. So the picture that you can see here on the right-hand side, this is what we call the front end of the optical parametric amplifier. And that is that's what gets used to seed the extra stages of the parametric amplifiers to increase the power of it. In this particular situation, we were developing parametric amplifiers that could go at 1.5 micron and at 3.1 micron. And the idea was these could be used for research into attosecond science and reaction microscopy. So whilst I was there, I also helped to develop the application lab for the attoscience experiments. But yeah, it was a little bit different to what I was used to. And working at an institute is also quite different to working at a university. For example, the type of teaching that I was doing was very different at a research institute. There was less sort of lab-based, there was less taught lab type teaching, and there was no lectures or anything. It was very much working with the masters and the PhD students in the lab. So then after about a year of working there, I decided that academia really wasn't for me, even though I'd given it a pretty good go. And I'd also been awarded, as I said, a Marie Curie fellowship at the time. So I had the opportunity to stay in academia, but quite honestly, I was getting a little bit bored, and I couldn't imagine my life of continuing just to develop lasers. I wanted to go in a different direction, and I probably could have done that in academia, but I would have been starting out on the bottom rung again. So I thought that maybe trying industry could be, I don't know, another route to learning something new. So this is when I started working for M2. Now, M2 is a photonics and quantum technology company, which is headquartered in Glasgow in the UK. But as I previously said, I was responsible for building up their Berlin office. So yeah, I was pretty much responsible for the expansion here in Germany. So that was finding lab and office space, finding a team, and then also the idea creation side of things. So we really wanted to have an innovation kind of office here in Berlin where we could do innovation or research and development projects. So yeah, I was developing their innovation strategy here in Germany. And that meant I would spend quite a lot of time writing grant proposals. In fact, I probably spent a good 60 to 70% of my time doing that. And I had to come up with the ideas for the projects. I had to come up with the ideas of how we could implement the projects and what kind of staff we needed and what kind of equipment we needed, all the things that go into coming up with an idea for research. The difference is the research has to end up going in the direction of developing a product in the end that can be sold by the company. So the type of research that I was doing was, like, generally speaking, split into 3 separate themes. Probably the most important theme, the theme that I spent most of my time doing was for this quantum technology. And this is kind of a buzzword around the world right now. And this was mostly in quantum sensing, quantum computing, and quantum enabled microscopy. The second most frequent field that I was working with, I would say, was the biophotonics, and helping their M-Squared's biophotonics division to find ways and novel things that they can do with their light sheet microscope and their label-free imaging approaches. And then finally, the third topic was chemical sensing, standoff detection, hyperspectral imaging, and basically detection of chemicals at a distance. I'm going to give a quick example of all 3 of these, and then I promise you that I'm coming to the end. So first of all, in the quantum. Now, there's a lot of funding available worldwide to bring quantum technology out of the lab and into the real world. So developing them into ultimately products, but really the first port of call is developing technology that is robust enough that it can be used out in the wilds. So the example we have here, I think this is a quantum navigation system. So this uses atom interferometry. So basically a cloud of ultra cold atoms that have been turned into an interferometer. And then this interferometer basically acts like an accelerometer, which you can basically determine the phase of the system as a whole. And then it will allow you to navigate through wherever you're going without the use of GPS. So the team in London actually turned this into something that was used in the real world. Here you can see it installed on a barge boat, which is then it was used to navigate through East London on this section of canals, which I think is really, really cool. Then the example in microscopy. So M-Squared have developed a light sheet microscope, which is quite different to a confocal microscope in that you have a 2-dimensional sheet of light, which is then scanned through your 3-dimensional sample. And the idea is you get much more rapid imaging of very delicate biological samples. Here is an example on the right-hand side of some samples that the light sheet microscope was used to image, and these are groups of organoids. Organoids are miniature organs that have been derived from stem cells, and they're thought to better mimic human physiology. So the organoids here, the top ones are before the organoids have been treated by a novel anti-cancer drug, and the ones on the bottom after the treatment. So I think it's a really nice way of visualizing how useful these sorts of technologies can be. Then finally, chemical sensing. So M-Squared have worked with the whiskey industry in Scotland. As we know, Scotland is very famous for whiskey. They have developed a handheld sensing device that can fingerprint and identify different whiskies. So it's really cool. They have been used to determine the different ages of the whiskies, the whiskies that have been aged in different barrels, and all sorts of things like this. And it's actually a really accurate way of being able to identify whiskey. So finally, getting to the concluding remarks, I wanted to end on some career tips and advice. What I wanted to say, most important, is to take chances on the opportunities that present themselves. I was very glad that I had the ability to take the chance on the opportunity of working in industry, because I've now found that it suits me a lot better, and I can say more about that later if people have questions. But yeah, don't be blind to opportunities when they come up. Decisions don't have to be forever decisions. Like, you can change. I've changed. I've oscillated through industry and academia and in, you know, universities and research institutes, and I've learned a lot more about myself in the process. And then, okay, so the heart can be fickle. What do I mean by this? Well, everyone says that you should be following your passions and what your heart wants, but actually, you know, your heart can change its mind. It's better to identify what are the things that you keep coming back to. What are the things where you start and maybe things didn't go that well, but you still want to go back to it. Try those things out, and you probably end up being much more satisfied in the end. And then finally, use your network. Optica, SPIE, the International Photonics Society, social media. Every job I've had, I've never actually had to apply for. I've got it via my network. And then, yeah, just a final thing about the Optica Ambassador Program. I know that I'm running out of, I'm definitely running overtime. I've had the opportunity to travel across the world and to meet so many amazing people. And I love to be able to talk with students and early career professionals across the world. So that's it. Final thoughts. I can't have a seminar without a picture of my cat. This is Pablo Neruda. Yeah, basically, laughter is the language of the soul. Do what makes you happy. Thank you very much, and sorry for overrunning.
Thank you very much, Dr. Gabriela. So if we can take at least like 1 minute, somebody have a question, we can check, right? I think all the advice that you have to give in your talk have been very useful for the attendants. We really appreciate that you have taken your time to show your career, right? Show your path in an optical career. And as you said, right, the mind can change. So you have a way to show the people that everything can be possible, even in academia or in the industry. So yeah. So we see here, do we have any questions? Just to check.
I think the Q&A box is empty, so I've answered all the questions without even being asked them.
Yeah, I think well, that was the thing.
Well, I have a few questions. I don't know if I can ask through here, or do I need to write it? Yep. Okay. Well, first of all, thank you, Gabrielle, for such an enlightening presentation, and obviously for coming and being here with us. I have a question about how you use lasers for remote sensing. And the question is about the information of the signal. What kind of information was provided with this sensing?
That's a great question. So basically for this vegetation LIDAR approach, we basically, well, the European Space Agency wanted to measure both the intensity change from the pulses when they get reflected back up to the satellite, and also any structure that was impacted onto the shape of the pulse, because we're sending down a very clean pulse, but that pulse ends up getting quite structured in the process of getting reflected back up. And also then the final thing that they measure is the time taken to get back up to the satellite, because basically the pulses that end up going down to the ground, they take longer to get back than the pulses reflected from the canopy. So basically, those are the three things that they're measuring.
Oh, okay, great. So it is kind of special sensing of the object on the surface.
It's very particular to the thing that they're trying to measure. There's another application of LIDAR, which is more atmospheric LIDAR, and they can do things like the structure of clouds and what gets reflected back and how that changes the pulse shape. But there's also another really cool thing called Doppler LIDAR, where they are measuring the speed of winds in the atmosphere. And that can help you to better predict if there's some kind of tornado coming or so on and so forth. And so basically this is basically working on the Doppler principle. So the winds that are going faster would reflect it and you'd get sort of time shifts and things like that.
Okay, great, thank you. I have another question about the alexandrite Well, it can be constructed to enable lasers with this kind of crystal. But are they? This is only for curiosity. Are they single light tuning or multi-light tuning lasers?
You can basically do both.
Okay.
It depends on the design of the laser cavity itself.
Oh, okay, great. And well, I guess that they can be used. I mean, is it available in Q switching mode, right? Because of the etymology of the word. And
yeah, so I was Q switching them. Well, I was developing CW, and I was also Q switching them to basically get the pulses that are required for remote sensing. But basically, yeah, you can also mode lock them and get ultra short pulses from them as well.
Okay. And well, my last thing, it is not a question. I just want to mention that was very interesting, this 2D scanning of samples, and of course using chemical sensing of whiskey, especially because it's UK. So yeah. Thank you so much.
Thank you very much.
Okay.
Okay. So thank you, Gabriela. We really appreciate your participation today here. So, okay, so let's go to the next.